Last section of the course, Chapter 19D, Solids of Revolution. So this is the last application of integration that we are going to be looking at. So if we look at a function, saying consider a curve y equals f of x, that means we're just looking at a function from a to b. If the shaded area below is revolved around the x-axis, so this is similar to what we had looked at before, area under a curve from a to b. We could determine that with the integral. But now if we take that curve and revolve it about the x-axis, it looks like this. Hard to draw in 2D, a 3D object, but something like that. We've revolved it 360 degrees about the x-axis, or 2 pi radians about the x-axis. A three-dimensional object is formed. Okay, this is called solid of revolution. We're going to learn how to calculate the volume of these. Volume of revolution. So we can use integration to find volumes of revolution. This is just the proof showing you why the formula exists the way it is. Basically what happens is if we took this example, okay, this shape, and we sliced out little discs here. Each of these little discs is as small as we can possibly make it. So dimension of h. Then we would have this formula for each of those sliced cylinders, pi r squared h, where h is the same for all of them, but the radius changes because this radius is changing as the curve changes. Okay, so pi r squared h. The leftmost disk would be, the radius would be f of a, and the rightmost disk, the radius would be f of b. So therefore all the middle disks would have radius of f of x, depending on what x is each time. This is actually a limit because we want those disks to be as small as we possibly can, and therefore that limit looks like this. Okay, here's our formula. As h approaches 0, in other words, we want each disk to be as small as we can possibly make it. Of course, it can't be 0 width, but as small as we possibly can. The sum of, from a to b, everything in here. So our integral looks like this. Pi times, and the reason we could take that pi value outside of the integral sign is because it's a constant value, pi. Pi times the integral from a to b of y squared, that's the radius squared, dx. There's our formula. When the region enclosed by a function and the x-axis and the vertical lines a to b is revolved about this x-axis, this is the formula. So just reiterating that is stating it again. So example 10, use integration to find the volume of the solid generated when the line y equals x from 1 to 4 is revolved through 2 pi around the x-axis. Okay, so first of all we need to know, what does this graph look like? Well, it's a diagonal line. Y-intercept 0, slope 1. We're going to revolve that. Now, we're only going to look at from 1 to 4 though. Okay, so we're looking from 1 to 4. So here's the part that we're revolving, and that's in pink. That volume is in pink. So the volume equals pi times the integral from a to b, so that's 1 to 4, of that function squared dx. And this will actually just give us the value. Simplify this, it's x squared dx, pi, take the integral, so x cubed over 3 from 1 to 4, pi, 4 cubed over 3, subtract 1 cubed over 3. Pi times 64 over 3, subtract 1 over 3, so 60. So pi times 63 over 3, which is, that's 21. So 21 pi is our answer. And we don't have units, so we use units, and it's a volume, so it's units cubed. So 21 pi units cubed. All right, so the last little piece of information that we need to talk about, volumes for two defining functions. So in other words, we're going to have an upper function and a lower function. And as you can see from this diagram, when we rotate both of those functions about the x-axis, our 3D object becomes something with a hole in the middle, so something like a donut. Okay, so we're going to need to define which function is upper and which function is lower. Here's just showing how that formula works. We're subtracting. It's basically the same volume formula, but we need to subtract the upper function squared. We need to do this operation. The upper function squared, subtract the lower function squared, and then take its integral. Okay, so for example, we might have something like this. We've got this function that's a curve. We've got this function that's a straight line. We want to rotate that, and this is what it ends up looking like. So let's do an example. Find the volume of revolution generated by revolving the region between y equals x squared and y equals the root of x about the x-axis. So again, we need to figure out which is the upper function, which is the lower function. So take a look at what that looks like. Y equals x squared is here. So that's actually the lower function. And y equals root of x is here, so that's the upper function. So the volume will be pi times from A to B. Okay, so from A to B, we need to figure out where do those graphs intersect. So they intersect here at 0, and they also intersect here at 1. And the way we would figure that out is by finding that point of intersection, setting those two graphs equal to each other. So I'm going to square both sides. So x to the 4th, subtract x equals 0. So x equals 0, and x cubed minus 1 equals 0. So x equals 1. Has to be positive 1, so it has to be 1. Okay, so there's our points of intersection, 0 and 1. That's where limits of our integral are, from 0 to 1. Upper function is the root of x squared. Subtract the lower function, x squared squared dx pi. Let's simplify this first. So this will be just x, and this will be x to the power of 4. We can now integrate x squared over 2, x to the 5th over 5, from 0 to 1. So pi 1 squared over 2, subtract 1 to the power of 5 over 5. And the other term will be 0. 1/2 minus 1/5, which is 5 tenths minus 2 tenths, 3 pi over 10 units cubed. Okay, excellent. Your last pieces of homework before your last assignment, 19D.1 and 19D.2. Please find those in your homework document and have fun.